Welcome to Unit 7, Lesson 11. What are perfect squares? Let's see how perfect squares make some equations easier to solve. Before I go over any of these, I really want you to try them. Each expression is written as a product of factors. You need to write an equivalent expression in standard form. So take a moment and tell me, what does that equal? And as you're doing this, I want you to think about what patterns emerge. And this last one kind of gives us a formula that we could follow. So start looking for some patterns. All right, go ahead and pause, try the problems, then we'll go over them. Okay, so you should have already tried this. So if I square 3x, we want to make sure that we're writing it out 2 times 3x times 3x. So we get 9x squared. All right, the next one we get 49x squared. The third one, now you may have used box method, you may have used distributive property. I know some teachers say the word FOIL, but we're trying to get away from that because it only works in limited number of situations. So x squared plus 4x adds up to 8x plus 16. Okay, here what do we get? X squared plus 2x plus 1. Here we get x squared minus 14x plus 49. So this is the tricky one. Like, what I'm curious to know what strategies you tried, but since you can't have a conversation with me right now, let's think about it. All right, you may have tried this strategy and wrote out a box and said, okay, x squared, this would be nx, this would be n number of x's, and n times n would be n squared. And then these two are like terms. So we end up with x squared plus n would be 2n's. It's a little confusing. 2nx, and then plus n squared. And that kind of gives us a formula. So let's look at, what does that formula even mean? Well, some of the patterns you may have noticed is, hey, if I have a 4 and a 4 here, oops, lost my pen. 4 and a 4 here. 4 times 4 is 16, and 4 plus 4 is 8. So if I double 4, I'll get to 8. And if I take 4 and square it, I get to 16. Let's see if that works for all of them. So this is saying if we double the n value, we get to this middle term. And if we square the n value, we get to that last term. So if I take 1 plus 1, I double it, I get to 2. If I take 1 times itself, I get to 1. So this is 1 squared, and this is 2 times 1. This is a neat pattern that emerges. That can be super helpful for us in the future. So here is that written out, right? We take the n, we double it. Uh-oh, I see one missing term. This should say an x here. Let's fix that. Okay. So we take the n value, we double it to put here, and we square it to go there. So why do you think the following expressions can be described as perfect squares? Well, I see trinomials. I don't see, so the only thing I see squared is this thing right here. Do you see anything else that's squared? Oh, you're right, the 9. Okay, the 9 is 3 squared. Okay, so we have x squared, we have 3 squared, and then this is 3 times 2, right? So this is 2 times 3x. So if I look at that and I compare it to this, I'll write it right below it. X squared plus, let me clear this line. I don't want anyone to think that that's a division, because that is not a division. So if I rewrite it below, x squared plus 2nx plus n squared, we can see, oh look, this aligns pretty nicely. Look, the 2, the 3, n is 3, n is 3. Okay, so it fits into this formula, and the formula says x plus n squared. So they're trying to say that, look, x plus 3 squared, that I could rewrite this trinomial as some binomial squared. All right. And like if we were to make one of those area diagrams, it would be an actual square. A lot of the times we're looking at like, really it's like a rectangle where this is longer and that's shorter. But for this one, it would definitely be a square because x plus 3 is the same length as x plus 3, and we would get an actual square. Okay, let's check on the next two. I'll take a second and see if you can find the perfect square and rewrite it as something squared. Go ahead, hit pause, try it yourself. Okay, you should have tried the next two. So here, let's see, what number squared gives me 64? Is that 8 times 8? And this is 8 times 2, 2 times 8. Oh, wait a second, that's not quite correct because it's not a positive 16, it's a negative 16. So 2 times a negative 8. And here, does a negative 8 squared still equal 64? Yeah, it does. Okay, so in this case, we have x minus 8. Let's double check. If I double negative 8, I get negative 16. If I square negative 8, I get 64. All right, so that is how I can rewrite that trinomial as a perfect square. And it really creates a perfect square, right? This side and this side are equal. It makes a square. Okay, if we're looking at the area model. The last one, this one's a little sneaky. It's got some fractions in it. Let's look at it carefully. So I want to ask myself, what times what equals 1 over 36? Well, I know 1 times 1 is 1, and what times what is 36? Well, 6 times 6 is 36. So it looks like to get 1 over 36, I'm going to have to multiply 1/6 and times itself. All right, now here, how did I get 1/3? Well, this formula says 2 times n. So what happens if I multiply 2 times n, which is 1/6? If I multiply those together, 2 times 1 is 2 over 6, simplifies to 1/3. Awesome. So we got 1/3. Another way to think about that is this middle term is 1/6 plus 1/6. 1/6 plus 1/6. And if we add them together, we get 2/6, and that simplifies to 1/3. Okay, so I have made quite the mess. Let me clear this up for you, and then we'll write the equation. Sorry about that. All right, so we decided that our n value is 1/6. So there's something squared. If we take x here and I have 1/6 there, it's a positive. If I square x plus 1/6, that quantity, I will get this trinomial. So that's why each of those is a perfect square, because the middle term is 2 times n, and the constant term is our n value squared. All right, thanks for watching.